Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. What happens when we have a variable in the base and a variable in the exponent? Forms like 0 to the power of 0, or infinity to the power of 0, or 1 to the power of infinity are incredibly deceptive. Your intuition might tell you that 1 to the power of infinity is just 1. But in calculus, that 1 is not 1. It's actually a limit that is approaching 1. And that infinity is a growth rate. So 1 to the power of infinity is a tug-of-war. And today, we're going to be using logarithms to settle the score. Now, before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first example, we're going to take a look at the case of 1 to the power of infinity. Notice here that as x approaches infinity, our base is approaching 1, and then our power here is approaching infinity. So the indeterminate form here is 1 to the power of infinity. But from the last video, we know that in order to use L'Hopital's rule, we need to either get it in the form of 0 over 0 or infinity over infinity. And the way to do that here is to use logarithms. So we start by taking the natural log of both sides, which means ln of L is equal to the limit as x approaches infinity of ln of 1 plus 1 over x to the power of x. Now using our log laws, we get this is equal to the limit as x approaches infinity of x times ln of 1 plus 1 over x. So we still haven't gotten it into the form that we want. This is currently in the form of infinity times 0. So the one extra step that is required is to bring the x down into 1 over x, which means this is the limit as x approaches infinity of ln of 1 plus 1 over x over 1 over x. So finally, this is now in the form of 0 over 0, and we can now apply L'Hopital's rule. So that means once we apply L'Hopital's rule, this is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x times negative 1 over x squared. So this is the derivative of the numerator. And now we take the derivative of the denominator separately, which is negative 1 over x squared. And since we have this common factor on the top and the bottom, we can cancel it out, which means we get this is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. And now we can evaluate this limit, and it is equal to 1. But notice that this is not what L is equal to. This is the natural log of L. So that means we need to do a final step. So we have ln of L is equal to 1. And to get rid of a natural log, we just need to go e to the power of each side. So this ends up being L is equal e to the power of 1, which is just e. So therefore, the limit here is equal to e. So now we see a nice limit definition for Euler's number. And it is quite a magical result because it came from something that looked like 1 to the power of infinity. For our next example, we're going to find the limit as x approaches 0 for x to the power of x. So here, the form that we have is 0 to the power of 0. And we're going to go ahead and follow the exact same process. We're going to take the natural log of both sides. So we get ln of L is equal to the limit as x approaches 0 from the positive side of x times ln of x. Again, this is not yet in an acceptable form, so let's go ahead and rewrite this into limit as x approaches 0 from the right-hand side of ln of x over 1 over x. And now this is in the form of infinity over infinity, which means we can go ahead and use L'Hopital's rule. And that is going to give us limit as x approaches 0 from the right-hand side of our numerator is now going to be 1 over x, and then our denominator is going to be negative 1 over x squared. Simplifying this is going to give us limit as x approaches 0 from the positive side of negative x. And this limit evaluates to 0. And again, don't forget that this is ln of L, so we have ln of L is equal to 0, which means L is equal to e to the power of 0, so therefore L is equal to 1. And now for the last example in this video, we want to find the limit as x approaches infinity of x to the power of 1 over x. So this one is in the form of infinity to the power of 0. And by now, you should know exactly how to start. We start by taking the natural log of both sides, so ln of L is equal to the limit as x approaches infinity of 1 over x times ln of x. Rewriting this into an acceptable format is going to give us limit as x approaches infinity of ln of x over x. So this is now in the form of infinity over infinity, which means we can go ahead and use L'Hopital's rule, and we get limit as x approaches infinity of 1 over x over 1. So now evaluating the limit is going to give us this is equal to 0. So therefore, we have ln of L is equal to 0, which means L is equal to e to the power of 0, which is 1. And now let's do a quick recap of what we covered in this video. The most common mistake that students make is forgetting that they have logged both sides to bring the exponent down. So once you find your limit, remember to exponentiate to your final answer. In this video, as well as the previous video, we saw quite a few one-sided limits, and this is necessary because ln of x isn't defined for negative numbers. And lastly, these limits look deceptive because there's a hierarchy of growth. E to the power of x grows much faster than polynomials, which grow faster than logs, which is why it's important for you to follow the steps outlined in this video instead of using your intuition. And now it is your turn to give this a try. Can you determine the limit on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.